by just saying that the work and ideas in this talk are based on many years of work with many people. And I particularly want to thank Andy Farrant, who I worked with on Karst at BGS for more than 20 years. And I also particularly want to thank Pete Smart and Tim Atkinson, who taught me so much about Karst and tracer tests. And many others have contributed to the things I'm going to show today. And I'm sorry if I've missed anyone important. Okay, so this is not one of the unusual karst aquifers of England. We'll get to that in a bit. But it is an example of some spectacular karst in Myanmar, which I was really fortunate to visit a few years ago in a brief period of relative political stability there. And this cave reminds me of the enormous volumes of water that can be transported through karst systems. The cave is called Elephant Whirlpool Cave. And if you visit it in the monsoon, I think it would look very, very different. And if you have a look here, you can see the tree trunks in the roof there, which are testament to the enormous floods that occur here. And Myanmar also illustrates the importance of karst for biodiversity as well. These spiders are big. If you look in the right there, you can see, whoops, I've done it again, sorry. See if I've got a, yeah, there. That's actually a gloved finger for scale. A very brave person, I think. And these spiders also run very fast, which is quite disconcerting. But we don't know very much about them. And in fact, they're really, really quite fascinating creatures, and they might be undescribed, they might be endemics. And it really shows that there is an awful lot still to learn about the biology of karst. And in Myanmar, we found a new species of cave fish. And we know it was new because there were no cave fish described in Myanmar before. In fact, the local villagers knew of these strange white fish, but they hadn't been described by scientists. And if you have a look, you can, uh-oh, what have I done now? Sorry, pressed the wrong button. Let me see if I can find them. Yes. Okay, so if you have a look, you can see the remnants of their eyes here. And we know that they're completely blind because they have no response to the bright lights that we're shining at them to take the picture. But they do have a good sense of smell. These are fish flakes, which we put into the pool, and that's how we found these fish. Okay, so even in the UK, we have an extraordinary groundwater fauna. And these are stigobitic invertebrates that are adapted to live underground. They have no eyes, they have no pigment, they also have long appendages so they can move around, and they have longer life cycles than their surface water equivalents as well. To give you an idea, in terms of size, they range from a few millimeters to over a centimeter in length. And we worked with biologists at Hull and Roehampton universities, and we discovered that the Nyphagus species are actually ancient endemics. Now, we don't have many endemics in the UK because most of our native species were wiped out by glaciations. But these Nyphagus species survived in groundwater. And we know that they diverged from their nearest relatives on the continent millions of years ago. So they must have been here for millions of years, which is really quite incredible. And I think as hydrogeologists, we mustn't forget that our UK aquifers are not just supplying water for us and supporting surface rivers and ecosystems, but they also support these unique groundwater ecosystems as well. And it's really great that the Environment Agency in England and NRW in Wales have recently started some stigobite monitoring programs as well. Okay, so stigobites are common in the chalk and the Jurassic limestones in England as well, which brings us to the main subject of the talk, which is the unusual karst aquifers of England. So I'm going to be focusing on the chalk and the Jurassic and Permian limestones. And the Permian limestones are dolomitic limestones that you might previously have known them as the magnesian limestone. So I'm going to give a short introduction and then I'll provide an overview of these three karst aquifers and then make some comparisons between them. And then I'll conclude by talking a little bit about some of the challenges and karst approaches that might help with them. Okay, so first, why unusual? And the main reason is that cave development is very limited. In these aquifers, caves are rare, they're short, they're small in comparison to many karst aquifers. So, for example, the well-known karst of the Carboniferous limestones in the UK have much longer caves than the chalk and the Jurassic and Permian limestones. And I've put some figures up in the table there. So in these karst aquifers, the karst networks are mostly made up of solutional fissures and smaller conduits. And here are some examples from borehole images. And the conduit on the left is about 20 centimeters high. So when conduits are large enough for humans to enter, we would call them caves at that point. Okay, so I'm not going to talk about the interesting question of the definition of karst, which is going to be one of the subjects of John's lecture this afternoon. But I do think it's very important how we perceive these aquifers. And whilst I think hydrogeologists have always known that the permeability of the chalk and the Jurassic and Permian limestones is about solutional enlargement of fractures, I think that it's fair to say that they perhaps haven't always considered this as karst. And people might think that rapid flow requires caves, but it doesn't. Mike Price showed that even for rapid flow over long distances of 6 kilometers, theoretically, this could be accounted for by a single pipe of only 74 centimeters diameter, or a smooth planar fissure, only 4.5 millimeters wide. So the important point here is that the permeability of these aquifers depends on networks of solutional fissures and conduits. And these fissures and conduits arise because of two main karst hydrogeological mechanisms. The first is stream sink to spring karst development, which probably most people here will be very familiar with. This is a conceptual cross-section through a karst cave system in the Mendips at Wookey Hole, and it illustrates this. So in karst areas, weakly acidic water enters the ground, and over time, the pathways between the input points and the output points evolve, and they get larger until there are networks of conduits between the stream sinks and the springs. And past karst systems formed in this way can also influence the modern-day hydrogeology, even when the stream sinks that created the karst systems are no longer active. The second mechanism is mixing corrosion, and this enables karst development at depth and in the absence of stream sinks. So the curve on the graph here shows how calcium carbonate saturation varies with the amount of PCO2 in the water. So waters with lower PCO2 reach saturation more quickly. And here there are two solutions, B and A, which are both fully saturated, but have different PCO2. And when they mix, the resulting solution, point C here, becomes undersaturated again. And this enables further dissolution. Okay, so a little bit of history. I wanted to say that karst features have been recognized in the chalk for a very long time. And in 1840, Long described some stream sinks, and he says, these rivulets pour down the tertiary clays until they arrive at the chalk, where they plunge into the ground and disappear. Karst features have also long been known in the Jurassic limestones, and this is from a speech in 1887 to the Cotswold Naturalists Field Club. After dinner, Mr. G.F. Plain made some remarks upon certain subsidences of the ground known as whirly pits. These subsidences, he found, were caused by water washing out the softer strata below, but it did not seem to be shown why these sinkings should assume always a more or less circular form. It appeared from the discussion which followed that like subsidences are known to occur in the Carboniferous limestone. I like that quote. And chalk karst caves were documented as early as 1908. William Coles Finch described a natural chamber over 17 feet high of considerable width and length. And from this, there is a natural adit through which a person can walk for about 60 feet. And these are his pictures of the karst passages that had been intersected during underground adit construction. They even did tracer tests in the mid-1800s. In 1864, Codrington writes, "There are several swallow holes near the junction of the chalk with the tertiary beds. From one of these, the water was traced by the late Mr. Blackwell, who coloured the water as it was swallowed up in the earth and witnessed its reappearance at the outlet at about the time expected," which left us guessing a little bit what that time might be. So there's quite a body of work on karst in these aquifers, and some examples are listed here. I'm not going to go through all of these now, but some of them will come up during the talk. And I think the important point is that despite this history of work, I think it's probably fair to say that many modern day hydrogeologists would not describe these as karst aquifers, and quite a lot of applied work has not considered karst or has been quite limited by a lack of karst data. So in 2016, I started a knowledge exchange fellowship, which was funded by NERC. And the aim was to really try and collate karst information and data and raise awareness of karst in these aquifers. And we looked at geomorphological and hydrogeological indicators of karst, so things like caves and stream sinks and tracer tests. And we divided the aquifers up into areas. And there are reports available online for many of these areas which provide details of the karst features and characteristics. And today I'm going to provide a broad overview of these karst aquifers with a bit more focus on the chalk, where we've done a lot of work over the last 20 years. Okay, so this map shows records of karst caves in the English chalk. The caves in the chalk are all small and they're all short. There are some slightly bigger and longer ones in the French chalk, but in England particularly, the cave development is very limited. The picture is actually a chalk cave beneath a stream sink in Reading, so actually not that far from London. The longest cave is Beachy Head Cave, which is 350 metres long. And this is the plan view of the cave survey. And you can see the cliff face with the entrances that have been exposed by coastal cliff retreat. And then the cave extends inland behind this. So Beachy Head Cave is obviously karstic, but in coastal cliffs, it can be quite hard to distinguish karst from marine caves. But quite interestingly, Terry Reeve visited the south coast over many decades, and he observed firsthand that new karst caves had been completely concealed behind the cliffs before, were then revealed by coastal erosion, and there's an example in the picture here. Okay, so in terms of recharge, there are three things in this map that I want to talk about. And the first is the importance of the chalk Paleogene margin in chalk karst development. So the pink areas on the map are these younger Paleogene deposits that overlie the chalk. And the red circles are stream sinks. And you can see that there's very high densities of these along the chalk Paleogene margin. The stream sinks tend to be fairly small, perhaps with flows of a few litres per second following persistent rain, a bit like the example in the picture here. But there are bigger ones, and there's one particularly important example, which is Water End in Hertfordshire. And this has an average flow of 80 litres per second and a capacity of 1,000 litres per second before it backs up and overflows. So this is massive. This is a QMEC, so completely comparable to the Carboniferous limestones. The second thing to consider is the glacial till deposits that overlie much of the eastern parts of the chalk outcrop. And where these are thick, there's no modern day recharge. But at the boundaries, again, streams can sink into the chalk. The till isn't shown on the map here, but the area in black is where many of these stream sinks have been mapped by Andy Farrant in the field. And these are generally smaller scale features than the stream sinks associated with the Paleogene margin. The third thing is the yellow triangles on the map. And these are some dry or losing sections of rivers which are crossing the chalk outcrop. And this is a very incomplete data set. But it would be useful to develop it further, I think, because the chalk rivers may be very big contributors to point recharge, and the sink points are indicative of where the solutional networks are underneath them. There can also be recharge via vertical solution features with no visible karst above at all on the surface. And you can see this in coastal exposures like these on the south coast. But I think away from the cliffs, it's very hard to know where these sorts of vertical fissures are, and we don't really know how frequently they occur. Okay, this map shows spring records for the chalk, and I think springs are really very important because they form the natural outlets for the karst networks. And there's lots of them, ranging from small seepages to huge outlets with flows of hundreds of litres per second. Many springs have very diminished flows or have even been lost because of the amount of abstraction from chalk boreholes, which often target the river valleys where the springs are. I think it's interesting that the chalk springs have received surprisingly little attention. There's not really much information on their discharges and their characteristics. Right, excuse me a minute, I'm just going to put my glasses on. Okay, that's a lot better. Okay, so some of the springs have quite typical karstic characteristics, like this example from Hungerford. And this is actually the spring where the tracer in 1886 arrived in about the time expected. So the left picture shows the spring under normal conditions, whilst the right one shows high turbidity following rainstorms, and this is reflecting the connectivity with stream sinks. And we actually did a tracer test from a stream sink a few kilometres from here, and the tracer arrived at the spring in about 14 hours. So interestingly, this is also about the time it takes for the spring to become turbid following rainfall. So perhaps this is what Codrington had noticed in 1864 and what he meant when he wrote that the tracer arrived in about the time expected, but we will never know. Other chalk springs are not connected to stream sinks, but have large flows indicating extensive karstic networks. And this is an ephemeral spring in Berkshire, which has peak seasonal flows of 700 litres a second, so quite big. And the river is dry for several kilometres downstream of here when the spring isn't active. And then the spring will suddenly start flowing and be reactivated. So it's really operating like a karst overflow spring. This map shows the locations of tracer tests that had been conducted in the chalk by 2021, with almost 100 individual connections demonstrated. Since then, Dan Matthews has done lots of tracer tests in Hertfordshire, which he's going to talk about later today. But I think the main thing to notice here is that there are many, many gaps. And in fact, in most catchments in the chalk, no tracer testing has been done. The tests that have been done are informative, though, and this is a plot of distance against velocity for the chalk tracer tests that were on the map. And these velocities are based on the first arrival of tracer. The different symbols represent different kinds of tests. And there are three things to notice. The first is that the tests demonstrate rapid flow, and in most of them, the flows were more than 100 metres per day. The second is the stream sink test. So these are the red and orange circles at the top right. And perhaps unsurprisingly, these tests have the most rapid velocities over the longest distances. And they're really far. Some are over 10 kilometres, and some are really fast, more than 10 kilometres per day. The final thing to notice is the velocities and distances in the test from the boreholes. So these are the triangles, and OBH is an observation borehole. So in these tests, the tracer was injected into the boreholes, not into a surface karst feature. And yet most of them show rapid flow. And I think, as Steve Worthington and Aidan Foley and John Gunn have all pointed out, the chalk velocities from tracer tests are comparable or even faster than what we see in many karst aquifers with extensive caves developed in them. Okay, we'll look briefly at 3 tests that illustrate some different points. And the first is a test we did to the Blue Pool in February 2005, so 20 years ago this month. And we injected just 610 grams of fluorescein dye, which really isn't very much for a tracer test. And it travelled the 5 kilometres to the Blue Pool in only 24 hours. And to our surprise, the pool was turned green, not what we were expecting. The concentration in the pool was only about 65 micrograms per litre, so unlikely to cause harm. But this does illustrate just how vulnerable these karst aquifers are and how attenuation can be very low. These are tracer tests from boreholes in the Yorkshire chalk carried out by Rob Ward and others at BGS in the 1990s. And these are interesting because they demonstrate flows of hundreds of meters per day over several kilometres, even though the injections were into boreholes. And Yorkshire is an interesting chalk area because there's no Paleogene cover, so the stream sinks seen along this boundary in southern England don't occur. The surface karst features are really very rare, and it's actually the hydrogeology that's indicative of the karst. As well as these tracer tests, some of the abstraction boreholes have very high transmissivities, more than 10,000 meters squared per day, which is suggesting extensive karstic networks in the saturated zone. And the coastal cliffs do provide some additional evidence of karst, with some big dissolution pipes exposed and also some cave entrances above sea level as well. Also in Yorkshire, there is tracer evidence of rapid flow through the unsaturated zone, and this was work done by Sam Alshorn at Leeds University. The tracer was injected at the surface, so not into a karst feature, and then it was detected in flowing fissures in underground mine workings. And these tests showed velocities of 10 to 20 meters per day, up to over 38 meters of unsaturated zone. And it's not just in Yorkshire that there's evidence for karst away from the Paleogene chalk margin, as shown in this map. So away from the margin, there are large springs, there's point recharge via streams and rivers, there's high transmissivities, there are some caves, and there are the rapid flows shown by the tracer tests. So although the chalk Paleogene margin is important for current stream sink to spring networks, there is evidence for karst throughout the whole of the chalk outcrop. So in fact, we can conclude that the chalk is karstic everywhere. But I think this is a good time to return to the question of why we might think of the chalk as an unusual karst aquifer and what its characteristics are that make it different from the Carboniferous limestones, apart from the lack of caves. And to do this, I want to think briefly about tracer recoveries and then to look at one chalk spring in a little bit more detail. Okay, so this is old data compiled in 2012, but it illustrates the point well, and I think it's unlikely that the story will change much when it's updated. And the main point is that although we've seen previously that the tracer tests show very rapid flow that's comparable to any karst aquifer, the tracer recoveries are often low. Yes, there are examples like the Blue Pool where the recoveries were high, but many chalk tracer tests, we're only just detecting tracer at the detection limit, and they have very low recoveries. And indeed, many tracer tests are unsuccessful, and it seems likely that in these unsuccessful tests, the high attenuation and dilution is the most probable explanation. So the chalk aquifer has a much higher attenuation than karst aquifers with more cave development. And this is partly because of dispersion into smaller voids, and also because of the high porosity of the chalk matrix, which enables diffusion between the karstic systems and the other parts of the porosity. I want to look in a bit more detail at the Bedhampton and Havant springs in southern England. And these are the largest chalk springs in the UK and maybe beyond. They have a mean flow of 1,100 litres per second, and they supply water to around 250,000 people. And just as an aside, they've recently been designated as a MICAS spring, one of the most important karst aquifer springs in the world. And this is an ongoing international project to identify important springs. And John Gunn has coordinated the UK effort on this. The Bedhampton and Havant springs have strong indicators of karst. They're connected to stream sinks developed along the Paleogene chalk margin. So these are the red circles on the map here, and the chalk is in green. The connections were demonstrated by tracer tests in the 1970s, led by Tim Atkinson, and they showed rapid velocities of up to 2.6 kilometers per day and high recoveries of around 70%, so showing really very low attenuation in this case. And then there were some further tests commissioned by Portsmouth Water, and in 2 of these, the velocities were actually more than 10 kilometers per day, so very fast. And there are karst features present throughout the catchment, and we can divide the catchment into 3 karst zones based on the distance from the Paleogene margin. This is a conceptual cross-section, and the chalk is shown in green. And you can see that there's runoff into the stream sinks, and these feed karst flow paths that passed under the Chichester syncline with thick Paleogene sediments overlying the chalk. And then the groundwater emerges at the springs. The springs also have water quality indicators of karst. So, for example, they have very high turbidity following rainfall. And a few years ago, we used the Bedhampton and Havant chalk springs as our UK karst spring example in a European study that aimed to develop methods of classifying karst springs and boreholes. And one method we tried was a vulnerability approach, applying scores to the springs based on factors indicating their vulnerability due to karst. So things like water quality indicators of karst or the presence of stream sinks or caves in the catchment. And this figure shows the scores on the y-axis for the different sites from across Europe, and each country had one site. The red triangles are the limestone springs, and these all had the highest scores, as might be expected, as did the one limestone borehole site, which is the larger pink circle here. The large green triangles are the 2 chalk springs, and Bedhampton and Havant had a very high score, which reflected the rapid flow from the tracer tests and the other strong indicators of karst. But the chalk spring from the Netherlands had a very low score. And then there were 3 dolomite springs, which had quite varying vulnerability. We also applied the method to 20 affinity water chalk boreholes in southern England, and these are the green circles. And you can see that these give a wide range of scores, and this suggests that the method is capturing the variability in the karst and the vulnerability variations in the chalk quite well. Okay, so the European study looked at lots of other methods of karst classification, and many of these considered spring flow responsiveness to rainfall. And I'm just going to show you one example output from the project. And this was actually looking at groundwater resource availability, and it's quite interesting. The mean discharge is on the y-axis. BH is Bedhampton and Havant, and you can see that it's one of the largest springs in the study with its mean flow of about a cubic. The x-axis is the memory effect based on Monjan 1984, and this provides an indication of spring response to rainfall. And you can see that the memory effect at Bedhampton and Havant is higher than it is in the other karst springs in the study. It's not shown here, but the coefficient of variation was also much lower at Bedhampton and Havant than in the other karst aquifers. So what this is showing is that whilst Bedhampton and Havant have strong indicators of karst and high vulnerability, they also have a much lower proportion of rapid recharge, which feeds them, than many karst springs. And I think this lower proportion of rapid recharge is an important characteristic of the chalk karst aquifer much more widely. Okay, so moving on to the Jurassic karst, this varies a lot across the country because there are big lithological variations in these limestones. And I'm going to give some examples from the 3 areas that we've done the most work on. And these are the Corallian limestones of Yorkshire, J1, the Lincolnshire limestone formation, J2, and the Great and Inferior oolites of southern England, J3. And I'll start in the north with J1. So the Corallian limestones of Yorkshire have very strong karst development. This is a Scalaba pot cave, which is almost 4 kilometres long, and it has quite big passages in it, as you can see here. There are lots of springs in the Corallian limestones. We don't have a good data set on these springs and their discharges, but this is a nice picture of Bog Hall Cave shortly before the water emerges from the spring. So very karstic. This area also has well-developed stream sinks and a high proportion of recharge via karst. And this map shows the Corallian limestone outcrop in purple across the middle. So as the rivers cross the outcrop, they sink into karst features. And the red circles show some of the major sinks. We don't have a full data set on these. But we do know that some of them are very big, with inputs of hundreds of litres per second, so big river sinks here. There has been some tracer testing in the Corallian limestone, and in particular, the most studied area is the Derwent catchment, which is in the east here. There. Okay. And here, Aidan Foley did lots of tracer tests from the Forge Valley swallow holes, and the connections are shown on the map here. Rapid flows were demonstrated, and the fastest was to Urton pumping borehole, which is here, and the velocity was 13 kilometers per day based on the time to peak, so really, really fast. And one thing I thought was quite interesting was that Foley et al. Estimated that 80 to 95% of the water at Urton is river water transported directly via the karst. So again, this is showing that we have a high proportion of rapid recharge in this aquifer. Moving south, the Lincolnshire limestone formation is quite different. There are no known caves here, and it's very unlikely that anything significant will be found. But there are smaller conduits, and you can see some examples in the pictures here. These are from a quarry in Lincolnshire that has intersected these conduits, and you can see the dissolutional scallops all down the walls from the past flows in these features. There are quite a few records of stream sinks. The circles on the map here show some locations. And the stream sinks seem to be associated with the boundary between the Lincolnshire limestone formation and the overlying glacial till deposits. But there are some stream sinks in the Great Oolite group as well. Some of the stream sinks are quite big. This is Eastern Wood Stream Sink, which was reported to have flows up to 300 litres a second. And you can see the turbidity here too, lots of sediment being washed into the aquifer. In the 1970s and the 1990s, tracer testing was carried out by students Ian Booker and Emma King with Tim Atkinson. And the map shows the connections that were proven, again with very rapid groundwater flow velocities. I'm sorry there's no scale bar here, but to give you an idea, the distance from Porter's Farm, which is here, to Ellsthorpe over here is about 12 kilometres. And so you can see that this connection crosses from the West Glen catchment to the East Glen. And these tests demonstrate the complexity of the karst networks and how they span different topographical catchments. And there's lots of divergent flow, and there's variable tracer recoveries with tracer recovered at different outlets, and also some quite big tracer losses as well. And there's also evidence of attenuation with long tracer breakthrough curved tails. So you can see here that in some tests, the tracer was still being discharged 100 days after it was injected. Moving south again to the main great and inferior oolite group area of southern England, this is the J3 area. And here there's lots of mass movement caves, but there are almost no karst caves. But there is still lots of evidence of karst, as we'll see. There are stream sinks, and we don't have a full data set on these again, but here are some records we do have. And I'm going to focus on two areas on this map, the river churn and stream sinks reported by Pete Smart. The river churn is an interesting example as there are records of an estival here. So this is a karst feature which acts as a sink under lower water level conditions and a spring under higher water level conditions. And the estival on the churn was described by Richardson in 1930, who said, "Water can be seen disappearing down swilly holes in the bed of the river, but when the water levels rise, water can be seen rising up through the swilly holes." And there are records of estivals in the Jurassic limestones and the chalk too, but data on these are quite limited. The river churn is also a really good example to show how lithology influences karst in this area. And this is a flow accretion profile down the river churn. And in the first 10 kilometres or so, there's fairly standard accretion as the river is flowing over the low permeability lias group. But then there are big losses as it crosses the inferior oolite aquifer, really big, almost a QMEC if you look at the scale here. And in fact, these arrows are actually surface water tributaries, so the losses are even more because there's some water coming in from the tributaries as well. Then there are springs at the junction with the low permeability Fuller's earth that result in big flow increases, and then more losses over the great oolite and forest marble limestones, and then further increases once the river flows onto the confining strata. So what you can see here is that geology is determining the locations of the karst features, where the stream sinks are, where the springs are, and influencing the hydrogeology of these aquifers. And Andy's going to talk much more this afternoon about geological influences on karst. The second thing I want to highlight here is the work of Pete Smart in the 1970s. So there are 15 stream sinks on this map, which were those reported by Pete. They're the bright green squares a little bit to the northeast of Bristol. And Pete did a huge amount of tracer testing here. He demonstrated 29 connections, most of them from stream sinks, a couple from boreholes. The results are similar to those we looked at in the Lincolnshire limestone in terms of flow velocities and recoveries and breakthrough curves, and also the complexity of the karst networks, as you can see in this map. But I think these are very important tracer tests because they show the karstic nature of the great oolite group, which is perhaps often a bit overlooked in hydrogeological studies. I'm going to talk now about Permian karst. So the Permian carbonates are dolomitic and used to be known as the magnesian limestone. And you can find the details on Permian karst in the recent P1 and P2 reports, and I'll just show a very brief overview here. One important factor is the presence of glacial till, particularly in the northern P1 area. And the till impacts modern day recharge, obviously, but it can also conceal older karst features where previously karst had been developed, but is now covered by those till deposits. But I think here, perhaps the most important factor is the role of the evaporite karst. And this has been really well documented by Tony Cooper and others. And you can see some examples of gypsum collapsed dolones in these pictures here. If you look at the geological sequence on the left, the carbonate strata are the Brotherton Formation and the Cadeby Formation. So these used to be called the upper and lower magnesian limestones. The Brotherton Formation is sandwiched between the Roxby Formation and the Edlington Formation, which both contain extensive gypsum karst. So there are lots of karst features in the Brotherton Formation which have formed because of collapse into the underlying gypsum karst. In contrast, the Cadeby Formation is below all the gypsum karsts, so not impacted in the same way. But from a hydrogeological perspective, there is connectivity between the Cadeby Formation and the overlying Edlington Formation. And this is shown in the conceptual cross-section at the bottom here. So I'm going to show you a few examples of karst in the carbonate rocks, so the Brotherton and the Cadeby. This is a big doline in the Brotherton Formation near Ripon in Yorkshire, and this was formed due to dissolution of underlying gypsum. This doline collapsed in 1939, and you can see the Brotherton Formation exposed at the back. And it's fed by sulfate-rich water, which is reflecting the connectivity with the gypsum. This map shows a compilation of evidence for karst in the southern Permian outcrop. And the older Cadeby Formation outcrops on the left. So this is carbonate karst, which is not caused by karst in the gypsum. And on the Cadeby Formation, there are some caves, there are some larger springs, and there are some stream sinks as well. This is a big cave entrance in the Creswell Gorge. And in fact, this gorge has intersected lots of relict karst carbonate caves. You can see it's quite a big feature. And the longest Permian carbonate cave is called Robin Hood Cave. It's 290 meters long, and you can see the distinctive solutional features in the roof. Now, the carbonate caves in the Permian are fossil caves. They don't have water in now. But what they do show is that conduit development of this scale can occur in the Permian dolomitic limestones. There are also some stream sinks into the Cadeby Formation, and here are some examples. You can see that they look like fairly typical small karst stream sinks. One of them is actually labelled Whirly Pit on the Ordnance Survey maps, which is a bit of a giveaway, perhaps. Okay, so hopefully this has given you a good overview of these three karst aquifers. And you can see that they all have all the classical karst features. They have stream sinks, springs, dolines, rapid flow, and solutional networks. And now I want to think a bit about comparison between karst aquifers. And in 1981, Atkinson and Smart suggested that the scale of karstification increases from the chalk through the Permian, Jurassic, and Carboniferous limestones. I think in some ways the recent work still supports this, but there are also some nuances, and I think it depends very much which karst factor you're thinking about and also which spatial scale you're looking at as well. So at the broad aquifer scale, in terms of rapid flow indicated by tracer tests, the chalk and the Jurassic and Carboniferous limestones can all have flows of thousands of meters per day. So in some ways, they're broadly comparable. If we consider cave development, we do see big differences, with much more cave development in the Carboniferous limestones, and then a bit more in the Jurassic limestones compared to the Permian and the chalk, which are similar. Aquifer storage also varies, with the least in the Carboniferous limestone and the most in the chalk. Glad I got that the right way around. In terms of stream sink sizes, which give an idea of the proportion of rapid recharge, there are many more larger stream sinks in the Carboniferous limestones. And then there's a general decrease from the Jurassic limestones to the chalk to the Permian. But these are broad patterns, and there's also a lot of regional variation. And I'm just going to show this in relation to two karst factors, caves and stream sinks. Okay, so here you can see our limestone areas, and you can see the known caves and the maximum cave lengths in the area. And basically what it shows is that there's a lot of variation. So you can see, for example, in the Jurassic limestones, there's a huge range from J1 and J4, which are the black squares here and here, which have caves of more than 1 kilometre, to areas J2 and J5 in the middle, which have no caves at all. So a lot of variability. If we look at stream sinks, the patterns are different to the patterns in cave development. Now, there are some data limitations in many of these areas for stream sinks, but we see differences between areas and differences compared to the caves, which I think mainly reflect real differences, not data issues. For example, in the chalk, there are very few stream sinks in the C1 area in the north and the C9 area in the south, but there are many stream sinks in the C4 and C6 areas, including some with inflows of more than 100 litres a second. I think an interesting observation is that there's not an obvious distinction between the chalk and the Jurassic limestones. There seems to be more variation within the Jurassic limestones and within the chalk than between them. But these are still quite big spatial areas, and there's also a lot of local variation within them. For example, the C3 area in the east has frequent stream sinks in the southwest of the area, but few elsewhere where there are thick glacial till deposits preventing recharge. So overall, I think we can conclude that there are some general patterns, but comparisons between these karst aquifers vary with spatial scale and depend on which karst factor is considered. And I've just looked at two here. The patterns are different if you look at dolenes or tracer tests or transmissivities or other factors. Okay, so we're reaching the end of this journey around the unusual karst aquifers of England. And in the last few minutes, I want to discuss some challenges that they pose and some karst approaches that might help. So we have karst aquifers in which there is little cave development. And like all karst aquifers, there's long-distance pollutant transport. And this can occur across topographical catchments, which makes it difficult to know where to target regulation and catchment management. I think that defining where the catchments of springs or boreholes are is really very difficult because we don't know where the solutional networks are. And I think this is particularly challenging in these karst aquifers because flow occurs in lots of smaller solutional networks rather than a few larger cave systems. And how can we know where the flow paths are when there are few caves that can be mapped? Okay, this is a tricky one, but the current source protection zones, which are our main tool in groundwater protection, I think it's fair to say that they do a pretty poor job in these karst aquifers. And I think this is because of the challenge in knowing where the solutional flow paths are, but also because the modelling methods that the source protection zones are based on are inconsistent with the karstic nature of these aquifers. They're just not able to represent the velocities and the heterogeneity that occurs in the karst. So there are lots of karst approaches that can help with these challenges, and I think that we're going to see a lot of these in today's programme. And I think a key one is developing good conceptual models of the catchments that take account of karst principles. So things like stream sink to spring karst pathways, mixing dissolution, karst inception horizons. And geology is really central to karst development. And I think you'll see a lot more of this later today with Andy Farrant, who will explain lots of examples of this. Numerical groundwater models need to be consistent with these conceptual models, which is a big challenge. But I do think that in the English karst aquifers, there is more scope for incorporating karst data like stream sinks into groundwater models. There's also the paper by Medici et al. That shows the need for very low effective porosities in groundwater models in these karst aquifers. And I don't know how widely these have been applied and how practical it is to apply them, but I think it's an important observation. And modelling isn't my area, but I do know that internationally there is a lot of work going on to develop better methods of groundwater modelling in karst. And one approach I've heard about is the Karst method, which was developed in Switzerland by Janine et al. And this method combines geology, karst, and groundwater data into groundwater modelling, which seems to be a good approach to some of these difficulties. Studies of borehole flows and borehole imaging are really useful for informing conceptual models because they enable identification of the depth of the flow horizons and the locations of the geological inception horizons controlling them and what those inception horizons are. I think tracer tests can be challenging in these karst aquifers because of the higher attenuation and dilution, which it makes it harder to detect the tracer. But they can tell us so much about where the flow paths are and what the flow paths are like. And you'll see some examples of this in Dan Matthews' talk about his tracer work, which has provided new understanding of the Hertfordshire chalk. I think maybe vulnerability risk-based approaches are quite useful in groundwater protection of karst aquifers, and they can be especially useful where we don't know where the flow paths are. So they enable regulation or catchment management to be focused on areas within catchments where it's more likely that pollutants could be transferred into the aquifer. So it doesn't matter quite so much if you don't know where all the individual flow paths are. Okay, how are we doing? 10 minutes. Okay, good. Well, perfect. We're getting to some final thoughts. And I think that we can conclude that we now have much more knowledge and data about karst in these aquifers, and we can use and expand on this to help with groundwater protection and management. I also think that in the time I've worked on karst, the pressures have got much greater. There's more demand for water resources. There are more impacts on surface streams and groundwater-dependent ecosystems. There's more development, creating more pollution. Groundwater quality is deteriorating, and new and emerging pollutants have been identified and need to be considered. And I think there's never been a time with more need for hydrogeologists with a good understanding of karst and for the application of karst approaches to groundwater problems. And it's really great to be here and to hear about all the work that's going on in the field. And I think I'm going to stop there and say thank you very much for listening to that.